So whilst we're talking about trig substitutions, I have mentioned this before. When you've got the square root situation, you have square root of two squares, so a squared plus x squared. By doing a trig substitution, you can turn the two terms into one term by using a trig identity. So if you've got a squared plus x squared, you'd substitute in an a tan theta, because you know tan squared plus 1 is sec squared. If you had an a squared minus x squared, you'd use, well, it doesn't matter, either sine or cos, because then you'd get a 1 minus sine squared or a 1 minus cos squared, and you could change that one. And the other situation, of course, is x squared minus a squared. In that case, use a sec theta, because then you'd get sec squared minus 1, which is tan squared. So let's show you where we get our standard integral from of the 1 on the square root of a squared plus x squared then. So I would do a tan theta, so dx is a sec squared theta to theta. Substitute in, the dx on the top becomes a sec squared theta to theta. The square root becomes a squared plus a squared tan squared, which we can change to a squared sec squared. The square root of a squared sec squared is a sec, which will cancel into the a sec squared on the top, leaving me with just the integral of sec theta. And we know the integral of sec theta, because remember, we're going to memorise that one rather than having to multiply top and bottom by sec theta plus tan theta. And we get the log of sec plus tan. I now just have to substitute back in. So I'll draw up a triangle so I can work out what these ratios are. Tan is x on a. The third side, remember, it's not a coincidence. It will turn out to be the square root of whatever you had in your original question. So reading off that, sec theta, square root of a squared plus x squared on a, tan theta is x on a, and you might be thinking, well, hang on, that's not the standard integral. Where's this plus, the over a comes from? Well, a is a constant. You could theoretically use your log laws and go minus log a, but hang on, log a is a constant, so really it is just plus a constant. So that's where the standard integral comes from. Now, I'm not suggesting that you would use this, but you could use this. I would hope when you see this one, you'd go, oh, hang on, x, derivative of x squared is 2x, I've got derivative times function here, and life's a lot easier. But we're in the middle of doing trig substitution, so you're thinking, oh, what shall I substitute? I'll make x equal to sine theta, so dx will be cos theta to theta. Let's sub all that in. X is sine theta, dx is cos theta to theta, over the square root of 1 minus sine squared. Well, 1 minus sine squared is cos squared, and the square root of cos squared is cos, leaving me with just the integral of sine. Integrate sine, we get minus cos. All right, draw myself up a triangle. So sine x over 1, third side, again, no coincidence, there is square root of 1 minus x squared. So reading off that, I can go, what's cosine again? Adjacent over hypotenuse, isn't it? Of course it is. But if I didn't remember, I've got the reference sheet, so that's good. So minus the square root of 1 minus x squared, and there's our answer. Yes, it is good if you recognise derivative times function. Let's try this one. Oh, you're going to love this one, trust me. You love this one. Square root of x squared plus 3. This is a good one. Okay, we'll go x equals the square root of 3 tan theta. So dx is root 3 sec squared theta to theta. Sub in. Oh. Nice, I told you were going to enjoy this. Yes, you've seen it already. But before we get to that nice second line there, or third line, second line of working. So substitute in for x squared plus 3, we get root 3 squared. I'll say 3 tan squared plus 3, which becomes 3 sec squared, square root of 3 sec squared, 3 sec, so I just bang did that all in one hit. The theta is the root 3 sec squared theta. Multiply together, and yes, we've got sec cubed, so you know what is about to happen. I'm going to change that to sec theta times sec squared. And we're going to do it by parts. U is sec theta, du is sec theta tan theta, dv is sec squared theta, so v is tan theta. And we get 3 times uv, sec theta tan theta, minus 3 times the integral of v du sec theta tan squared theta. Okay, now sec theta tan squared theta. Well, I can split that up because tan squared is sec squared minus 1. So I split that up, it becomes sec cubed plus 3 sec theta. Now, the integral of sec is the log of sec plus tan. And sec cubed, oh, that's what I'm trying to work out. That's okay. Get my little triangle and sub back in. Now be careful when you sub back in, because you see my 3 times the integral of sec cubed theta? That is equal to the square root of x squared plus 3. So I've substituted in for 3 integral sec cubed theta, the square root of x squared plus 3. Which means 2 lots of the square root of x squared plus 3 is that wonderful expression there. I can divide everything by 2. In fact, I don't really need the square root of 3 on the bottom of the logs there. Get rid of them. Who wants them? Doesn't really matter if you put them there or not. I've just absorbed it as part of the constant. And there's the answer. I told you were going to like that one. Let's add some more in.